Welcome to the lecture 24 of the course Modeling and TCAD Simulation of Solar Cell. In this lecture, we will focus on organic solar cell and a perovskite solar cell. In last lecture, we have discussed thin film solar cell, that is second generation solar cell, where we have seen the thickness of absorber layer is very less, in the order of 1 to 4 micron, and the absorption coefficient of the absorber layer should be much high to absorb most of the light intensity within a short length. The requirement or importance of thin film solar cell also we have discussed, particularly for flexible applications. Thin film solar cell is the best option. We have also discussed cadmium telluride, copper indium gallium selenide, amorphous silicon based thin film solar cells, their structures, and band alignment in case of cadmium telluride and copper indium gallium selenide materials. We have also discussed challenges of thin film solar cell, and we have seen that toxicity and stability, these are the main issues associated with the thin film solar cell. In the third generation of solar cell, that is organic dye-sensitized solar cells, nanostructured solar cells, etc., and recently evolved perovskite solar cell have been under consideration of researchers. So in this lecture, we will discuss the basic working principle of organic solar cell. Organic solar cell behaves differently from the semiconductor based solar cell in terms of photovoltaic generation. That will be discussed here. Some advantages of organic solar cells will also be discussed in this lecture. And the perovskite solar cell, which is very important nowadays, and it has attracted lots of interest among researchers in today's world. That will be discussed in detail. Also, the challenges of perovskite solar cells will be covered. First, let us discuss the working principle of solar photovoltaic cell in organic material. There are four main processes for generation of photovoltaic in organic solar cell. First one, it is light absorption and exciton generation. Here one thing you can observe, in earlier lectures we have used the term electron hole pair generation, but here we are using exciton generation. This is applicable for solar cell consisting of organic materials, because in organic materials excitons are generated than electron hole pairs. Because in case of organic solar cell, if light is incident on organic material, excitons are generated, and these excitons have a high binding energy. Let us first concentrate on the matter, what is exciton and what is the difference between electron hole pairs and exciton. And to understand the exciton in case of organic material, instead of valence band and conduction band concept, here people used to have HOMO and LUMO. HOMO means highest occupied molecular orbital, which is analogous to the valence band, and LUMO means lowest unoccupied molecular orbital. When light is incident on organic material, electrons are excited from HOMO to LUMO. That is analogous to transition from valence band to conduction band in case of semiconductor material. Let us first draw the band position in a organic material, and we will discuss what is the exciton. Suppose this is highest occupied molecular orbital and this is lowest unoccupied molecular orbital. When light is incident, electron transits from HOMO to LUMO, but these electron hole pairs we are not calling as a electron hole pair. We are calling it as a exciton because these electron and hole, they are bound, weakly bound. Binding force between these two is weak, but they are bound. This is called exciton. So exciton is nothing but weakly bound electron hole pair. Bound means it has some binding energy. Exciton binding energy is a term which indicates the energy required to dissociate these exciton to make electron hole pair free. Free electron hole pairs means they can conduct current, conduct electricity. So exciton binding energy in case of semiconductor material is in the range of 2 to 10 milli electron volt. But in case of organic materials, it is high. So for semiconductor material, since the binding energy is only 2 to 10 milli electron volt, and you see the thermal energy at room temperature, KT, that is 25.85 milli electron volt. So in case of semiconductor material, initially when excitons are generated on incident of light, these excitons can easily dissociated to electron hole pairs by thermal energy. But in case of organic material, binding energy of exciton is high. High means higher than, say, KT value at room temperature. So in that case, thermal energy at room temperature is not sufficient to dissociate the exciton to electron hole pairs. That's why in case of organic solar cell, we need some material called donor and acceptors to dissociate the exciton to electron hole pair. So the binding energy, exciton binding energy for semiconductor material is 2 to 10 milli electron volt, whereas KT value at room temperature is 25.85 milli electron volt, which is sufficient to dissociate exciton. This is the difference between semiconductor material and organic material. So in the first process, in case of organic solar cell, on incident of light, the light energy is absorbed by the material and excitons are generated. Next process is excitant diffusion. Actually, donor and acceptor materials need to be blended to the active material, and donor and acceptor has some energy. Say acceptor and donor always try to donates electrons, and acceptor which like to take electrons. So when this excitant reaches to these donor and acceptor materials, they get some force which can dissociate them from weakly bound to free. So that's why in case of organic solar cell, donor and acceptor materials need to be blended within the active material. Next, another important thing is excitants in organic materials have a very short diffusion length. Diffusion length meaning is the thing that average length which can traverse by excitant before they get recombined. It is related to the average lifetime. That is the average time after their generation they remains alive. And within this time they diffuse by some force due to concentration gradient, and obviously the length covered by this time is called diffusion length. In case of organic materials, the diffusion length of the excitant is very less. That means average exciton lifetime is also very less, because ln is proportional to root over of tau n. This is in the order of 10 nanometer only. That means you have to dissociate the excitant before traversing the 10 nanometer distance, but that is quickly after generation of excitant. So this is a challenge. So active layer is often designed as a bulk heterojunction so that it can dissociate. That means acceptor donor automatically mixed within the active material. This is called bulk heterojunction. Means not the junction between two different layers. Bulk heterojunction means material consists of both type of materials. That is a donor type, acceptor type. So as a bulk it is acting as a heterojunction. This is called bulk heterojunction. So a nanoscale blend of donor and acceptor materials to maximize interface area is also to dissociate this is required. Nanoscale blend means in molecular level they have to mixed on donor and acceptor. That's why we will show you the organic materials. They consist of different elements within it. So the excitant diffusion is the next process. So after generation, excitant will start diffuse, but within 10 nanometer on average you have to dissociate them, otherwise they will be lost. The third process is excitant dissociation, that already I discussed. At the donor acceptor interface means in a single compound material donor acceptors are mixed. So there are some locations where you can get donor acceptor interfaces within the material itself, within the bulk heterojunction itself. And the difference in energy levels between this donor and acceptor, they have some energy level difference. So due to energy level difference, there is a gradient of potential or energy is there, and that energy will help to dissociate the excitant or split the excitant before their recombination. And the electron transfers to the acceptor, because acceptor is ready to accept the electrons and donor ready to donate the electrons. That means electron transfers to the acceptor material while the hole stays in the donor material. This is a very important thing. Electron transfers to the acceptor material, and hole remain with the donor. The next state is charge transport and collection. The separated charges, that is free electron and hole, which already done in exciton dissociation. Exciton dissociation, that is electron transferred to the acceptor and hole remains with the donor. So the separated these charges, the electron and hole, travel through their respective materials to the electrodes. That is acceptor material and donor material. The electron hole traverse with these acceptors and donors to the electrodes. Electrons flow to the cathode and holes flow to the anode. And this flow of charge carriers generates the electric current. So there is a difficult type of mechanism. So if you see the structure, let us see the structure of a organic solar cell. The material, which is P dot PSS, is a nothing but conductive polymer. This is an active material. This is very important material. P dot means actually this particular combination is a composition, and this conductive polymer, and PSS is another polymer, and this is acting as a charge balancing or counter ion and dispersant. With these two in combination act as a active material. You see, you start with a glass substrate again, because these are all thin, very low thickness. To give the mechanical stability, you should start with a glass substrate. Then transparent conducting oxide layer is deposited. On top of that is P dot PSS and P3HT-CNT. This P3HT-CNT is another material, is a blend of polymer P3HT and carbon nanotubes. This mixture of these two, P3HT is a polymer, is a famous polymer, and carbon nanotube, this is called P3HT-CNT. And P dot PSS, this mixture, P dot is a polymer and PSS is also polymer. This is styrene sulfonate. So they are in this layer. And on top there is a contact. So ultimately light is incident from the bottom side. P3HT acts as a donor material and CNT act as a acceptors. You see, I mentioned earlier that there is a mixture or blending of donor and acceptor. So P3HT, CNT, this is the donor acceptor blended material, where CNT acts as a electron acceptors and P3HT as a donor. So these material, this CNT can help dissociate excitons, because the acceptor will accept the electrons and hole will remain with the donor material. And CNT, that's why, can act as an acceptor to accept the electrons. The excitons are generated in the P dot PSS and they are basically dissociated and separated in the P3HT CNT process. Perovskite is an example of organic solar cell. Perovskite is a material which is basically in the mineral group, that is mineral perovskite, CaTiO3. The name from this mineral perovskite, it comes, the perovskite material, a derivative of the perovskite. This perovskite material acts as a light absorbing or active layer in case of perovskite solar cell. It has a nature that high absorption coefficient. Its absorption coefficient is very high. This is the main advantage of this perovskite solar cell. At the same time, it has good electrical property also. That's why people have been exploring the prospect of this perovskite material as a successful development of organic solar cell. And is a low cost production also is possible. Even at room temperature you can deposit it through a chemical process So a large area production is also feasible for this perovskite solar cell. It has all advantages except one thing, that is its stability issue. This material, named after the mineral perovskite, CaTiO3, is typically a metal halide perovskite. Metal halide perovskite with a crystal structure similar to this material. And methyl ammonium lead iodide, this is the very common perovskite material used for perovskite solar cell. Its symbol is CH3NH3PbI3. But due to presence of this lead, this is toxic. People are trying to remove the Pb to replace the lead by different another suitable alternative materials. Anyway, this is abbreviated as methyl ammonium lead iodide, PbI3. And this perovskite material acts as an active material in case of solar cell. So let us see the structure. First, the structure, it is on glass substrate. Two layers which are very important in this organic solar cell is called electron transport layer. Sometimes it is called ETL. Another is hole transport layer or HTL. And there is a contact on top of the hole transport layer. Light is incident from this layer. In perovskite, absorber is sandwiched between two layers. There is a hole transport layer and electron transport layer. And this electron transport layer, some contact is made from this layer. Again, the technique is the same like others. Like earlier we discussed that some area of electron transport layer on the some surface area on top of the electron transport layer is left for making contact, and in the rest portion other layers are deposited. That's why the front contact is shown here. Another contact, gold contact is generally used, is taken from the hole transport layer. Now, sunlight absorbed by the perovskite layer, which is active layer in solar cell, I already mentioned. And this absorption excites the electrons within the perovskite materials, raising them to a higher energy level and creating electron hole pairs. Electron hole pairs or exciton, electron hole pairs, because already in the perovskite there are several compositions are there. So the energy to dissociate the exciton is already obtained from this material itself. And if you see the band position, that is very important for perovskite solar cell, particularly the electron transport layer and hole transport layer. This is perovskite in the middle. This pyro, this is another polymer. So this is nothing but acting as a hole transport layer, and ITO, this is acting as a electron transport layer. Sometimes zinc oxide also used, or aluminum doped zinc oxide also used. So light is incident from this side. This is a transparent, so light can be passed through this layer, and the contact position also you see. So mainly electron holes which are generated in this layer. So electrons are coming to this contact, and the band position is like that. It has no offsets, it is facing. Similarly, the holes also not facing the offset value. So this separation, the charge separation, there is a and extraction, this occurs in these transport layers. The excited electrons and holes are separated by the perovskite material's unique properties. That is the difference from the other organic materials in the perovskite. Here automatically these are separated due to the inherent nature of this donor acceptor interface property within the perovskite. And these charges are efficiently transported away from the perovskite layer by two layers, there is electron transport layer and hole transport layer, and these basically facilitate the flow of electrons and holes to the respective electrodes. So choice of the thickness of perovskite layer is another important parameter to study, because this is organic material basically. So lots of defect centers are there, and if you increase the thickness of the perovskite, it will create more and more electrons and holes. That is the chance of increasing the photocurrent. But at the same time, you should remember the trap centers or defect centers will be increased with increasing the thickness of this perovskite layer. So there is a choice of thickness of perovskite layer should be optimum. Also, the force at the interface between perovskite and hole transport layer and perovskite and electron transport layer, they are also important in terms of carrier separation. So if we have more and more thick perovskite absorber layer, so the excitons generated at the middle portion, they may be recombined before reaching to the interface between perovskite layer and hole transport layer and perovskite layer and electron transport layer. So choice of thickness of perovskite layer is important, and also choice of electron transport layer and hole transport layer important, because they should not face any interface. Rather, electron cannot flow in this direction due to the barrier present here, and hole also cannot move towards the ITO side due to presence of the barrier in this case, this interface between perovskite and ITO. This is a typical structure of a perovskite solar cell. Different types of electron transport layer and hole transport layer are being explored by researchers to enhance the performance of the device. Choice of contact materials is also important. Although gold serves as a good contact for this case, but is a costly. So an alternative also, mixture of contacts are being also used. And main concern of the perovskite solar cell is the stability. That will be coming the next. So these are the challenges of organic solar cell. First of all, very low power conversion efficiency. Though it is very easy to fabricate, too easy to deposit, you can have very small apparatus to develop the organic solar cell. But low conversion efficiency is mainly due to the narrow absorption range. Only a small portion of the solar radiation can be harvested or can be utilized by the organic materials. Second reason is very low charge carrier mobility, which limits how well charge move to the electrodes. Mobility is also very less because so many scatterings occur. Scattering means one type of collision between electrons, holes to the atoms, to the molecules, etc. So since electrons and holes possess the wave nature as per quantum mechanical phenomena, so instead of collision, the classical thing we use as a scattering. So due to scattering, the mobility is very less in case of organic materials, which is another reason to limit the efficiency. High exciton binding energy. So this I already mentioned, at room temperature it is not possible to dissociate them. That's why some special arrangement or a mixture of donor acceptor interface is required to dissociate the exciton to electron hole pairs. Stability and lifetime, because organic materials are easily affected or stability and lifetime. Stability and lifetime of organic materials is really an issue because organic materials are prone to reaction to the environment due to humidity, due to different gases present in presence of sunlight, and it degrades the efficiency of solar cell based on organic materials. In environment you have oxygen, moisture, ultraviolet radiation. So this can ultraviolet radiation can act as a stimuli for the reaction. So this leads to a short operational lifetime, that is only 5 to 10 years, even less than that. In case of perovskite, only 30 days is sufficient to degrade the performance almost 50%. Whereas in case of single crystal silicon solar cell, it is 25 years. This is a really challenge for organic solar cell to compete with the single crystal solar cell. Encapsulation is another technique to protect the reaction or of organic material with the environment, but it can help out to some extent, not fully, but it increases cost and complexity. Scalability and reproducibility, that is another challenge. In case of organic material, if you test the repeatability, that is if you develop 5 samples successively, there may not be same performance always. So this is very questionable, the reproducibility. And lab scale device production often use the spin coating techniques, spin coating like techniques or small area fabrication methods. But scaling up to roll printing, just like thin film solar cell, flexible solar cell we have discussed, or large area modules, while maintaining the performance, is still difficult. Uniform coating is also a bit difficult. Controlling the defects is also important. And large scale encapsulation, which is the solution for protecting the materials to be reacted, to be affected by the environmental elements, that is also costly in case of solar cell. Charge transport and collection losses, mismatch of energy levels and electrodes, that means you have to choose the materials very precisely and very optimally so that the interface works properly. Interface cannot obstacle the charge flow, but it can help to flow the carrier in a desired direction, or it helps to dissociate the electrons and holes from the exciter. So these are design is very challenging. So ultimately in this lecture we have discussed the basic principle of organic solar cell. We have seen that exciton plays an important role in case of organic materials because on incident of light, weakly bound electron hole pairs are generated in organic materials, and binding energy of this exciton is much higher than the binding energy of exciton in semiconductor material. That's why we need to have a special arrangement to dissociate these exciton to electron hole pairs and to get the electrical conduction. Until and unless we can dissociate them, we cannot get the electrical conduction. And for that, a donor acceptor interface is required. So in active material, in case of organic solar cell, is a combination of 2 to 3 types of materials consisting of donor and acceptor. That is called bulk heterojunction. Charge transport and charge separation up to the electrodes is also challenge. Lots of scattering occurred in case of organic solar cell. Diffusion length of the perovskite, diffusion length of the excitons is very less. We have to dissociate them very quickly after their generation. And challenges are These challenges have already been discussed. And perovskite solar cell, a typical structure we have discussed also. And importance of electron transport layer and hole transport layer are also discussed in this lecture. These are the references you can follow for organic solar cell. Thank you.